1905, Bern, Switzerland. At this moment in history, the universe as we understood it was beginning to fracture. For centuries, the bedrock of science had been Newtonian, a world of predictable orbits, solid objects, and absolute certainty. If you knew the position and velocity of every particle in the cosmos, you could, in theory, predict the future with perfect precision. But beneath the surface of this orderly reality, a chaotic, invisible storm was brewing. Enter Albert Einstein, a young patent clerk with a mind capable of seeing through the veil of classical physics. Einstein began to dismantle the old guard. With his work on the photoelectric effect, he proposed something radical. That light was not just a continuous wave, but was composed of discrete packets of energy, which we now call photons. He had introduced the concept of the quantum. This wasn't just a mathematical curiosity. It was a fundamental shift in how we perceived reality. It suggested that at the most microscopic level, the universe was not smooth, but granular. But Einstein's most profound contribution to the coming nuclear age was his realization of the profound link between energy and matter. In his most famous equation, E equals mc2, he revealed a terrifying truth. Matter is simply incredibly concentrated energy. A tiny amount of mass, if unlocked, could release a staggering, almost unimaginable amount of power. He had provided the theoretical blueprint for the sun, and inadvertently for the bomb. As Einstein opened the door to the subatomic world, another titan was walking through it. In Copenhagen, Niels Bohr was constructing a new model of the atom itself. Before Bohr, the atom was often envisioned as a tiny solar system, with electrons orbiting a nucleus like planets around a sun. Bohr realized this couldn't be right. He proposed that electrons exist in specific, quantized energy levels. They don't drift, they jump. They exist in one state, and then, through a process called a quantum leap, they vanish and reappear in another. This quantum revolution was a period of intellectual vertigo. The more these scientists looked into the heart of the atom, the more the world seemed to defy common sense. They discovered that particles could behave like waves, and waves could behave like particles. They found that at the quantum level, nothing was certain, only probabilities. This era was defined by a series of intense, often heated debates between the giants of the field. Einstein, ever the seeker of absolute truth, struggled with the inherent randomness of this new physics, famously declaring that God does not play dice with the universe. Bohr, however, embraced the chaos, arguing that we must accept a reality that is fundamentally probabilistic. To the casual observer in the early 1900s, these were merely abstract philosophical debates played out in university lecture halls. They seemed disconnected from the grit and grime of human existence. But these men were not just debating the nature of reality. They were mapping the internal architecture of the very building blocks of existence. They were discovering the rules of a game that humanity was not yet prepared to play. Without this revolution, without the understanding of energy-mass equivalence and the quantized nature of the atom, the subsequent discovery of nuclear fission would have been impossible. The stage was being set, the laws were being written, and the door to the atomic age was being pushed open, one quantum leap at a time. 1911, Manchester, England. If the quantum revolution had provided the rules of the game, the next decade would provide the map of the playing field. For years, the scientific community had been operating under a profound misunderstanding of what an atom actually was. They believed the atom was a solid, indivisible sphere, a tiny, uniform marble of matter. But the reality was far more complex, and far more hollow. The man who would shatter this illusion was Ernest Rutherford. Working in the laboratory at the University of Manchester, Rutherford embarked on an experiment that would fundamentally change our conception of reality. He took a sample of gold foil, thinner than a human hair, and bombarded it with alpha particles, which are high-energy, positively charged particles. According to the prevailing models of the time, these particles should have passed through the foil like bullets through tissue paper, encountering only minor deflections. But as Rutherford observed the results, he saw something that defied all logic. While most particles passed through, a small fraction of them didn't just deflect, they bounced straight back, as if they had struck a stone wall. It was a moment of pure, scientific shock. Rutherford famously remarked that it was as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. This anomaly forced a radical new conclusion. The atom was not a solid mass. Instead, it was almost entirely empty space. At its very center lay a tiny, incredibly dense core, a nucleus. This nucleus contained nearly all the atom's mass, concentrated into a space so small it was nearly inconceivable. This discovery gave birth to the planetary model of the atom, but it left a glaring structural mystery. If the nucleus was positively charged, and the electrons orbiting it were also positive, why didn't the entire structure fly apart? Why did matter hold together at all? The answer began to emerge through a frantic, global race to identify the components of this central core. In 1919, Rutherford succeeded in proving that the nucleus was not a singular entity, but was composed of smaller, fundamental particles, the protons. He had essentially performed the first instance of transmutation, turning one element into another by altering its atomic nucleus. Yet a mathematical crisis remained. The atomic weights of elements did not match the sum of their protons. There was a missing piece of the puzzle, a ghost in the machine. Scientists knew there had to be something else inside the nucleus to account for the mass, something that possessed no electrical charge. For over a decade, this neutral particle remained a theoretical necessity, a phantom waiting to be caught. It wasn't until 1932, in the laboratories of Cambridge, that James Chadwick finally captured the ghost. By bombarding beryllium with alpha particles, he observed a radiation that was neither light nor electrical in nature, but possessed immense mass. He had discovered the neutron. This was the final piece of the structural puzzle. The nucleus was revealed as a crowded, chaotic cluster of protons and neutrons, held together by forces that human intuition could barely grasp. But this discovery was more than just a triumph of chemistry. By identifying the neutron, a particle with mass but no charge, science had inadvertently discovered the ultimate key. The neutron was a projectile that could penetrate the nucleus without being repelled by its electrical field. The map was complete. The target was identified. The door to the nucleus was no longer just ajar. It was standing wide open. December 1938, Berlin, Germany. The stage was set. The components of the atom were known, the neutron had been captured, and the theoretical doorway to the nucleus was wide open. But the scientific world was still operating under a fundamental assumption, that if you bombarded a heavy nucleus with a neutron, you might knock a piece off, or perhaps nudge it into a slightly heavier element. No one, not even the most daring physicists, imagined that the nucleus could be completely shattered. At the Kaiser Wilhelm Institute for Chemistry, the collaboration between Otto Hahn and Lise Meitner was one of the most formidable in scientific history. Hahn was a master chemist, precise and methodical. Maitner was a brilliant theoretical physicist, the intellectual engine that drove their partnership. For years, they had worked side by side, pushing the boundaries of what was possible. But as the shadow of the Nazi regime lengthened over Germany, the partnership was violently severed. Maitner, being of Jewish descent, was forced to flee her homeland, escaping to Sweden in a desperate midnight flight. Left behind in Berlin, Hahn continued the experiments. He and his assistant, Fritz Strassmann, were attempting to bombard uranium, the heaviest element known at the time, with neutrons. They were looking for transuranic elements, something even heavier than uranium. But as the results came in from the laboratory, Hahn was met not with discovery but with confusion. The chemical analysis was impossible. The bombardment of uranium had not produced something heavier. Instead, the results showed traces of barium, an element that was significantly lighter than uranium. To a chemist like Hahn, this was a scientific absurdity. It was as if you had fired a cannonball at a heavy boulder, and instead of a dent, you were left with a pile of pebbles. It defied the laws of chemistry as they were understood. Hahn, puzzled and perhaps even doubting his own data, wrote to Maitner in Sweden. He reached out to the one person who possessed the mathematical intuition to make sense of the chaos. In the snowy isolation of Sweden, Maitner sat with her nephew, Otto Frisch. They pored over Hahn's letters, dissecting the chemical data through the lens of physics. It was Maitner who had the radical epiphany. She realized that the uranium nucleus was not a solid, impenetrable sphere, but a fragile, liquid-like drop of energy. She theorized that the neutron hadn't just chipped the nucleus. It had caused the entire structure to oscillate violently before splitting in two. She applied Einstein's famous equation, E equals mc2, to the mass lost during this split. The math was staggering. The tiny amount of mass that vanished during the division was converted into a massive, terrifying amount of kinetic energy. They had found it. The process was called nuclear fission. In that moment of quiet calculation in Sweden, the world changed forever. The discovery of fission proved that the atom was not just a building block of matter, but a reservoir of unimaginable power. The ghostly neutron had become a key that could unlock the very heart of the universe. But as Maitner and Hahn celebrated this triumph of human intellect, they were unaware that they had just handed humanity the blueprint for its own potential destruction. The era of the atom had ended. The era of the bomb had begun. London, January 1939. While the scientific community was still reeling from the implications of fission, a different kind of storm was brewing in the mind of a Hungarian physicist named Leo Szilard. Szilard was not a man of quiet contemplation. He was a restless, intuitive thinker, a man whose mind moved with the speed of the very particles he studied. He had already been working on the idea of neutron bombardment for years, but the news from Berlin had acted like a lightning strike, illuminating a dark and terrifying path that no one else had yet dared to walk. As the details of Maitner and Hahn's discovery trickled through the international scientific grapevine, Szilard sat in his study, the mathematical elegance of fission transforming into a visceral, waking nightmare. He began to play a mental game of what if. He imagined a single neutron striking a uranium nucleus. He pictured the nucleus splitting, as Maitner had described, releasing a burst of energy. But then, Szillard's mind went one step further. He realized that the split wouldn't just release energy. It would release more than just light and heat. It would release more neutrons. This was the moment of the realization, the aha moment that would haunt him for the rest of his life. If those newly released neutrons were to strike neighboring uranium nuclei, and if those nuclei in turn split and released even more neutrons, a self-sustaining cycle would begin. A geometric progression of destruction, a chain reaction. Szilard saw it clearly. A single event could trigger a cascade of trillions of microscopic explosions, all occurring in a fraction of a second. He wasn't just looking at a new way to power a city or a new way to understand the stars. He was looking at a way to harness the fundamental binding force of the universe to create a weapon of unprecedented, apocalyptic scale. He sat in the silence of his room, perhaps looking out at the London streets, realizing that the very fabric of civilization was now fragile. The physics was no longer abstract. It was political. It was existential. The implications were immediate and suffocating. If the laws of physics allowed for a chain reaction, then the race to control it had already begun. And in the current geopolitical climate, the question wasn't if a nation would attempt to build such a device, but which nation would get there first. Szilard knew the geography of the world was shifting. The Nazi regime was expanding its grip across Europe, and the scientific elite of Germany, men and women who had once been the vanguard of human progress, were now working under the shadow of a totalitarian state. If Hitler's scientists mastered the chain reaction, the balance of power would not just shift, it would be obliterated. For Szilard, the discovery of fission was not a victory for science. It was a terrifying responsibility. The ghostly neutron had been transformed from a tool of discovery into a trigger for catastrophe. He realized that the scientific community could no longer remain in its ivory tower, detached from the movements of armies and the ambitions of dictators. The chain reaction had been conceived in the mind of a physicist, but its consequences would soon be felt by every living soul on Earth. The spark had been struck. Now, the world had to decide if it would be used to light the way forward or to burn everything to the ground. August 1939, Princeton, New Jersey. The theoretical nightmare that had taken root in Leo Szilard's mind in London was now a frantic, driving mission. He knew that scientific insight, no matter how profound, was useless if it remained confined to the lecture halls of Europe. The race was not merely between laboratories. It was a race between ideologies. To prevent a Nazi monopoly on the atom, Szilard realized he needed more than just equations. He needed the weight of a superpower behind him. But Szilard was a physicist, not a diplomat. He lacked the political stature to command the attention of the world's most powerful leaders. To bridge that gap, he needed a name that carried the weight of the universe itself. He needed Albert Einstein. The meeting between the two men was a collision of two different worlds. Szilard, the restless, pragmatic strategist, and Einstein, the icon of pure, abstract thought. For Einstein, the concept of the chain reaction was a profound disruption of the cosmic order he had spent his life studying. Yet, as Szilard laid out the terrifying mathematics of uranium fission, the philosopher-scientist felt the cold grip of reality. The abstract beauty of E equals mc2 was being stripped of its elegance and recast as a blueprint for annihilation. Together, they began to draft a document that would change the course of human history. It was not a scientific paper. It was a desperate plea. They chose their words with agonizing precision, crafting a letter that was part warning, part prophecy, and part ultimatum. They did not send it to a scientific journal. They sent it to the White House. On August 2, 1939, the letter arrived on the desk of President Franklin D. Roosevelt. It was signed by Einstein, but it was the intellect and the urgency of Szilard that pulsed through every sentence. The letter informed the president that the discovery of fission had opened a door that could never be closed. It warned that extremely important scientific progress had been made in Germany, and that the possibility of constructing extremely powerful bombs in a few months was no longer a matter of speculation, but a looming reality. The letter was a direct challenge to the American conscience. It argued that the United States could not afford to be a bystander, while the Third Reich harnessed the energy of the sun to fuel its war machine. It demanded that the government take immediate, decisive action to investigate the potential for atomic weapons and to secure the necessary resources for their development. When the letter reached Roosevelt, the atmosphere in the Oval Office shifted. The president was a man of cautious diplomacy, but the implications of the Einstein-Szilard letter were impossible to ignore. This was no longer a matter of theoretical physics or academic debate. This was a matter of national survival. The letter acted as the catalyst, the sudden spark that ignited the fuse of what would become the Manhattan Project. It forced the hand of the American government, pulling the gears of industry, military, and science into a singular, massive, and secret machine. The warning had been delivered. The door to the atomic age had been kicked open. And as the letter moved from the hands of a physicist to the hands of a president, the world began its descent into a new and terrifying era of existence. September 1939, Berlin, Germany. While the halls of the White House echoed with the sudden, frantic urgency of the Einstein-Szilard letter, a darker reality was already manifesting across the Atlantic. The shadows cast by the swastika were lengthening, and for the scientific community, those shadows were filled with a terrifying ambiguity. The rise of Nazi Germany was not just a political upheaval. It was a fundamental disruption of the global intellectual landscape. For decades, science had been a borderless endeavor. The Republic of Letters allowed physicists in Berlin, Copenhagen, Paris, and Princeton to exchange ideas with a fluidity that defied national identity. But the Nazi regime had shattered that sanctuary. Under the Nuremberg laws and the ideological cleansing of Deutsche Physik, a movement that sought to purge Jewish science from German universities, the very fabric of international cooperation was being torn apart. As the Nazi Party consolidated power, a massive, involuntary migration began. Some of the greatest minds of the 20th century, men like Enrico Fermi, Edward Teller, and Hans Bethe, found themselves fleeing a continent that had turned hostile to their very existence. They were refugees of intellect, carrying with them the most sensitive secrets of the subatomic world. To the Allied powers, this exodus was a double-edged sword. It was a loss of talent for Europe, but a massive, unexpected infusion of genius into the United States. Yet, as these scientists crossed the ocean, a chilling question haunted them. What was happening in the laboratories they had left behind? In Germany, the scientific infrastructure remained formidable. The Kaiser Wilhelm Institute was one of the most advanced research hubs on the planet. While the Nazi regime was ideologically driven, the German military machine was fueled by an obsession with technological superiority. The regime's pursuit of Wunderwaffen, wonder weapons, was not merely propaganda, it was a strategic doctrine. If the Germans could harness the energy of the atom, the war would not just be won, it would be ended in a single, cataclysmic stroke. This uncertainty created a psychological climate of pure paranoia. In the United States, the fear was no longer about a theoretical possibility. It was about a race against a clock that was already ticking. Every intelligence report regarding German industrial capacity, every rumor of a secret facility in the Black Forest, and every movement of German heavy water shipments added fuel to the fire of American anxiety. The rise of the Third Reich had fundamentally changed the why of nuclear research. It was no longer a pursuit of pure knowledge or a quest to understand the building blocks of the universe. It had become a desperate, defensive scramble. The scientific race had been weaponized by the geopolitical reality of a totalitarian superpower rising in the heart of Europe. The Americans realized that they were not just researching a new form of energy, they were attempting to build a shield before the hammer fell. The shadow of Nazi Germany had stripped away the luxury of scientific caution. It had replaced the contemplative pace of the laboratory with the frantic, high-stakes rhythm of a global sprint. The race was no longer a possibility, it was a necessity for survival. And in this race, there would be no silver medal. There would only be the winner, and those who were consumed by the fire. May 1943, Santa Fe, New Mexico. The transition from theoretical fear to industrial reality required more than just intellect. It required space, isolation, and an unprecedented level of secrecy. The United States government, operating under the umbrella of the Manhattan Project, realized that the work being done in small university laboratories was no longer sufficient. To build a weapon of this magnitude, they needed to create a world unto themselves, a place where the laws of physics could be harnessed away from the prying eyes of enemy spies and the unsuspecting gaze of the American public. That place would be a desolate, high-altitude plateau in the Jemez Mountains, a location chosen for its rugged terrain and its distance from any major population center. This was the birth of Los Alamos. To the outside world, the project was a ghost. To the thousands of people being moved into the New Mexico desert, it was a mystery. This wasn't just the construction of a laboratory. It was the rapid, feverish assembly of a secret city. In a matter of months, a landscape of sagebrush and dust was transformed into a sprawling complex of wooden barracks, reinforced concrete laboratories, and high-security fences. The logistics were a nightmare of wartime mobilization. Every road leading into the site was monitored. Every telegram was intercepted. The military, led by the uncompromising General Leslie Groves, imposed a regime of strict compartmentalization. If you worked on the enrichment of uranium, you were forbidden from knowing the details of the plutonium research. Even the workers building the houses often had no idea what the men in the white lab coats were actually calculating. At the center of this whirlwind was a man who embodied the duality of the project, Robert Oppenheimer, a brilliant, somewhat eccentric theoretical physicist with a penchant for literature and philosophy. Oppenheimer was tasked with the impossible, turning the abstract mathematics of fission into a functioning, deliverable weapon. Under his leadership, Los Alamos became a crucible. It was a melting pot of the world's greatest and most conflicted minds. Nobel laureates lived alongside junior technicians. Refugees from Nazi Europe lived alongside American soldiers. But the creation of Los Alamos was more than a feat of engineering. It was a psychological experiment. For the scientists, the isolation was profound. They were living in a vacuum, stripped of their families, their social lives, and the comfort of knowing whether their work was a contribution to peace or a harbinger of doom. The desert heat, the biting winter winds, and the constant pressure of the ticking clock created a claustrophobic atmosphere of intense intellectual labor. As the houses were framed and the laboratories were wired, a new kind of society emerged, a society built entirely around a single, terrifying purpose. The secret city was a microcosm of the war itself, a place where the highest aspirations of human genius were being harnessed to serve the most destructive ends imaginable. The foundations were laid. The scientists were in place. The infrastructure of the atomic age was rising from the new Mexican sand. But as the city hummed with the sound of construction and the quiet scratch of pencils on paper, the question remained. Once they successfully harnessed the atom, would they be able to control the fire they had so desperately worked to ignite? Late 1943, Oak Ridge, Tennessee. If Los Alamos was the brain of the Manhattan Project, then Oak Ridge was its massive, throbbing heart. While Oppenheimer and his team wrestled with the elegant mathematics of the explosion, a much more brutal, industrial problem loomed over the project: the fuel. To trigger a chain reaction, the scientists couldn't use just any uranium. In nature, uranium exists primarily as two isotopes, uranium-238 and uranium. The 238 is stable, abundant, and useless for a bomb. The 235 is the prize, the fissile material capable of sustaining a runaway reaction. But there is a catch that borders on the impossible. For every 10,000 atoms of uranium mined from the Earth, only one of them is the precious 235. The challenge was not just a scientific one, it was an elemental one. Because these two isotopes are chemically identical, they cannot be separated by any traditional chemical reaction. They are twins, separated by nothing more than the weight of three tiny neutrons. To isolate the 235, the Manhattan Project had to find a way to exploit the microscopic differences in their mass. They had to perform a feat of modern alchemy, separating matter based on the weight of an atom. The scale of the undertaking was staggering. The government poured billions of dollars, an astronomical sum in the 1940s, into a sprawling, top-secret industrial complex in the Tennessee Valley. This was not a laboratory. It was a landscape of gargantuan, windowless factories that hummed with a terrifying, mechanical hunger. The first attempt was a process known as electromagnetic separation. At the Y-12 plant, massive, towering machines called calutrons used intense magnetic fields to whip uranium ions through a vacuum. The heavier 238 atoms would follow a wider arc, while the lighter, more volatile 235 atoms would veer closer to the center, allowing them to be collected. It was a brute force method, incredibly slow and consuming massive amounts of electricity, but it was the first hope of the project. Simultaneously, engineers were developing gaseous diffusion. This required the construction of the K-25 plant, at the time, the largest building in the entire world. The process involved forcing uranium hexafluoride gas through miles of microscopic porous membranes. The lighter 235 molecules would pass through the pores slightly faster than the 238, slowly, agonizingly slowly, accumulating the necessary concentration. The struggle was defined by failure. Early prototypes leaked, membranes clogged, and the sheer physics of the gases proved more temperamental than anyone had anticipated. There were moments when the project teetered on the edge of collapse, with the enrichment rates falling far behind the urgent timeline dictated by the war in Europe. In Oak Ridge, the air was thick with the tension of a race against time. Thousands of workers, many of them young women recruited from across the country, operated these colossal machines under a veil of absolute silence. They were moving mountains of ore to extract a handful of dust. They were fighting a war against the very structure of matter itself. Every ounce of enriched uranium produced was a hard-won victory in a battle where the enemy was not a person, but the stubborn, fundamental laws of the universe. Late 1943, Hanford, Washington. While the massive, windowless factories of Oak Ridge were straining to refine uranium, a different kind of miracle was being forged in the desolate, windswept landscape of the Columbia River Basin. If Oak Ridge was the project's attempt to refine what nature provided, Hanford was an attempt to bypass nature entirely. The scientists at Los Alamos were facing a terrifying reality. The enrichment processes at Oak Ridge were agonizingly slow. Even with the gargantuan K-25 and Y-12 plants, the yield of uranium was nowhere near what was required for a reliable weapon. The math was cold and unforgiving. To build a bomb that was small enough to be delivered by an aircraft, but powerful enough to change the course of history, they needed a more efficient fuel. They needed something more concentrated, something more potent than the enriched uranium they were currently struggling to harvest. They needed a shortcut through the periodic table. The plan was as audacious as it was dangerous. Instead of trying to separate isotopes of an existing element, the Manhattan Project would use a nuclear reactor to transmute one element into another. The goal was to take uranium-238, the useless, stable isotope that made up the vast majority of natural uranium, and bombard it with neutrons. Under the intense, controlled fury of a nuclear fission reaction, these neutrons would be absorbed by the 238 atoms, causing them to undergo a transformation. They would shed a beta particle, an electron, and in doing so, they would become something entirely new. They were going to perform true, modern alchemy, turning uranium into plutonium. To achieve this, the engineers constructed the B reactor, the world's first large-scale nuclear production reactor. It was a monstrous, steel-clad beast, designed to sit in the middle of the Hanford site, isolated from the world. Unlike the experimental reactors of the past, the B reactor was built for one purpose: industrial-scale transmutation. It was a machine designed to cook uranium in a bath of radiation, churning out a new, synthetic element. But the discovery of plutonium presented a new, even more complex set of problems. While plutonium-239 was the holy grail, a fissile material far more efficient than uranium, it was also incredibly difficult to handle. It was highly radioactive, chemically volatile, and intensely toxic. Once the B reactor had finished its work, the newly created plutonium couldn't simply be poured into a container. It had to be chemically separated from the highly radioactive, spent, uranium fuel. This necessitated the construction of a massive, terrifyingly complex chemical separation plant. Workers here were dealing with liquids so radioactive they could kill a man in minutes if a single valve failed or a single pipe leaked. The scale of the Hanford site was expanding into a sprawling, invisible empire of concrete and steel, all dedicated to the extraction of a few grams of a substance that had never before existed in the history of the universe. As the B reactor went critical for the first time, the implications were profound. The Manhattan Project was no longer just refining the materials of the Earth. It was manufacturing the very essence of destruction. The plutonium path had been cleared. The scientists had found their shortcut, but in doing so, they had unlocked a new, even more volatile chapter in the race to build the ultimate weapon. July 16, 1945, Jornada del Muerto, New Mexico. The desert was silent, save for the low hum of heavy machinery and the restless wind sweeping across the salt flats of the Jornada del Muerto. For months, this stretch of wasteland had been transformed into a fortress of secrecy. This was not just a testing ground. It was the threshold of a new era. The plutonium harvested from the reactors at Hanford had finally arrived at Los Alamos, processed into a dense, heavy sphere of metal. But the scientists faced a final, terrifying uncertainty. They had the fuel, and they had the mathematics, but they did not truly know if the physics would hold. Would the implosion mechanism work? Would the plutonium compress with enough force to trigger a self-sustaining chain reaction? Or would it merely sputter and fail, a multi-billion-dollar dud in the sand? The device, codenamed the Gadget, sat perched atop a 100-foot steel tower. It was a masterpiece of lethal engineering, a complex assembly of high explosives designed to squeeze a plutonium core with such unimaginable speed and symmetry that it would achieve criticality in a fraction of a microsecond. As the countdown began, the atmosphere was thick with a tension that transcended mere scientific curiosity. It was existential. In the bunkers below, the men and women of the Manhattan Project waited. There were no cheers, no celebratory music, only the heavy, rhythmic breathing of people who knew they were about to witness something that could never be unseen. They were waiting to see if they had mastered the atom, or if they had simply invited a demon to the table. At 5:29 a.m., the world changed. The explosion was not merely a sound. It was a physical blow that shook the very foundations of the Earth. A blinding, white-hot flash, brighter than 1,000 suns, scoured the desert, turning the midnight sky into an artificial noon. For a fleeting moment, the darkness of the New Mexico desert was annihilated. Then came the fire. A colossal, rising pillar of incandescent plasma surged toward the heavens, a mushroom cloud of terrifying proportions born from the sudden release of energy that defied human comprehension. The heat was so intense that it turned the desert sand into a glowing, green glass. The shockwave followed, a wall of compressed air that tore through the landscape, a physical manifestation of the power that had just been unleashed. In the silence that followed the roar, a profound realization settled over the observers. Oppenheimer, watching the spectacle through the haze of heat and dust, famously recalled the words from the Bhagavad Gita, "Now I am become death, the destroyer of worlds." The Trinity test was a success. The physics had worked. The implosion had been perfect. But as the glowing embers of the gadget cooled in the desert heat, the triumph was hollowed out by a sudden, chilling dread. The barrier had been breached. The transition from theoretical physics to practical devastation was complete. The scientists had proven that humanity could indeed unlock the energy of the stars, but they had also proven that we now possess the means to erase our own civilization. The desert was no longer just a wasteland. It was the birthplace of the atomic age, an age defined by a power that was as magnificent as it was monstrous. August 6, 1945, Hiroshima, Japan. The blinding light of the Trinity test had been a proof of concept, a singular moment of scientific validation in the isolation of the New Mexico desert. But the world was about to learn that the success of the gadget was only the beginning of a much more terrifying reality, the era of the deployed weapon. While the gadget had been a laboratory experiment, the weapons destined for the Pacific theater were designed for one thing: mass-scale delivery and total annihilation. To understand the scale of the devastation that followed, one must understand that the Manhattan Project had not developed a single type of bomb, but two fundamentally different methods of achieving the same catastrophic end. These were the gun type and the implosion type designs, the little boy and the gadget. The first, little boy, was a marvel of deceptive simplicity. It utilized uranium, an isotope that had been painstakingly enriched through the massive industrial efforts at Oak Ridge. The physics of the gun-type design was straightforward, almost mechanical. It functioned much like a literal cannon. Inside a long steel barrel, a solid slug of enriched uranium was propelled by a conventional explosive charge toward a stationary target of uranium. When the two masses met, they combined to form a supercritical mass, a quantity of fuel so dense and large that a self-sustaining chain reaction became inevitable. Because uranium is relatively easy to manage in this configuration, the design was considered conservative. The scientists at Los Alamos were so confident in the gun-type method that they did not even bother to test it before deploying it. They knew it would work. It was a crude, reliable, and terrifyingly efficient way to deliver a nuclear payload. The second method, which we had just witnessed at Trinity, was far more sophisticated and infinitely more dangerous. The implosion-type design used plutonium. Unlike uranium, plutonium cannot be used in a simple gun-type mechanism. The physics of its fission rate is too volatile. If you tried to shoot plutonium at another piece of plutonium, the weapon would likely fizzle, exploding prematurely with only a fraction of its intended power. To harness plutonium, the scientists had to invent something entirely new: implosion. Instead of a gun, they used a sphere of plutonium surrounded by a precisely engineered shell of high explosives. The goal was to create a perfectly symmetrical shockwave that would compress the plutonium core inward, crushing it to several times its original density. This compression was what forced the atoms so close together that the chain reaction would ignite. This was the method of the gadget, and it was a masterpiece of high-stakes precision engineering. When Little Boy was dropped from the Enola Gay, it represented the triumph of industrial scale and reliable physics. When the gadget exploded at Trinity, it represented the triumph of complex, cutting-edge science. One was a sledgehammer, the other was a surgical strike of unimaginable force. As the mushroom cloud rose over Hiroshima, the distinction between these two methods became academic. Whether through the simple momentum of a uranium slug or the violent compression of a plutonium core, the result was the same: the sudden, violent unmaking of a city and the permanent alteration of the human condition. August 6, 1945, Hiroshima, Japan. At 8:15 a.m., the morning sun was just beginning to illuminate a city of nearly 300,000 people. There was no warning, no siren, and no shadow of a plane to signal the end of the world as they knew it. From the belly of the Enola Gay, a single B-29 bomber released Little Boy. As the uranium slug met its target thousands of feet above the city, the conservative physics the scientists had relied upon transformed from a mathematical certainty into a visceral, hellish reality. In a fraction of a second, the temperature at the hypocenter soared to several million degrees Celsius, hotter than the surface of the sun. The heat flash was so intense that it didn't just burn, it vaporized. People within the immediate radius were turned into shadows, their very existence erased before their nerves could even register pain. Those who survived the initial thermal pulse were met with a secondary, more crushing force, the blast wave. A wall of compressed air, moving faster than the speed of sound, leveled reinforced concrete buildings and turned debris into lethal shrapnel, scouring the landscape of everything that stood. As the mushroom cloud rose, it carried with it a toxic shroud of radioactive fallout. This was the true dawn of the nuclear era, the realization that the weapon did not just destroy what it touched, but poisoned the very environment itself. In the days and weeks that followed, the survivors, known as hibakusha, began to suffer from a new, invisible killer, radiation sickness. Nausea, hair loss, and internal bleeding became the hallmarks of a catastrophe that defied traditional medical understanding. The success of the Manhattan Project had achieved its tactical goal of ending the war, but it had done so by introducing a form of violence that was fundamentally inhuman. But the world was not finished being introduced to this new reality. August 9, 1945, Nagasaki, Japan. 3 days after the devastation of Hiroshima, the United States prepared to deploy its second, more sophisticated weapon. This was no gun-type device. This was the Fat Man, the plutonium implosion bomb, the sibling of the Trinity test. While the target city of Nagasaki was geographically different, nestled in a valley that partially shielded it from the blast, the result was a terrifyingly similar echo of the first strike. The implosion mechanism worked with devastating precision. The high explosives compressed the plutonium core, triggering a massive release of energy that dwarfed the Hiroshima explosion in sheer concentrated power. Once again, the sky was torn asunder. Once again, a city was transformed into a landscape of ash and twisted steel. The sheer scale of the two bombings in such rapid succession forced a global reckoning. The war in the Pacific would soon end, but a new, invisible conflict was being born. The immediate impact of Hiroshima and Nagasaki was more than just the destruction of two Japanese cities. It was the shattering of the human psyche. The era of conventional warfare, of bullets, bombs, and bayonets, had been superseded by the era of the absolute. The political landscape of the world shifted overnight. The United States now stood as the world's sole nuclear superpower, possessing a weapon that could dictate the terms of global existence. The threshold of what was possible in combat had been crossed, and as the smoke cleared over Japan, the world realized that humanity had finally mastered the power to destroy itself. August 1, 1949, Semipalatinsk, Kazakhstan. For 4 years, a heavy, suffocating silence had hung over the geopolitical stage. The United States, holding a monopoly on atomic fire, had entered a period of unprecedented, almost arrogant dominance. To the leaders in Washington, the atomic age was an American age. They believed their technological lead was a permanent fortress, a wall that would keep the growing shadow of the Soviet Union at bay. But beneath the surface of the burgeoning Cold War, a frantic, desperate race was being waged in the secrecy of the Ural Mountains and the frozen wastes of Siberia. While the West celebrated its monopoly, the Soviet Union was engaged in a monumental feat of espionage and industrial mobilization. Through a vast network of intelligence assets, most notably the spy Klaus Fuchs, who had worked within the very heart of the Manhattan Project, the Kremlin had obtained the blueprints of the American secret. They didn't just know that a bomb was possible, they knew how it worked. They knew the mathematics of enrichment. They knew the chemistry of plutonium. The world waited with bated breath, sensing that the era of American uniqueness was nearing its expiration date. On this day in 1949, that tension snapped. At approximately 1:00 p.m., a device codenamed RDS-1, or First Lightning, was detonated at a testing site in the Kazakh steppe. The explosion was not a mere imitation of Western technology. It was a profound geopolitical earthquake. In an instant, the American monopoly was shattered. The monolith of Western security had been cracked, and the realization rippled through the halls of power from the Pentagon to the Kremlin. The nuclear age would not be a solo performance. It would be a duet of destruction. The successful Soviet test fundamentally altered the calculus of global power. The United States was no longer the sole arbiter of human survival. The Iron Curtain, a term famously coined by Winston Churchill to describe the ideological and physical divide between East and West, had now been reinforced with radioactive steel. The division of the world was no longer just about maps, borders, or political philosophies. It was about the distribution of catastrophic potential. This event triggered an immediate and frantic escalation. In Washington, the shock gave way to a sense of profound vulnerability. The realization that the Soviet Union could achieve parity so quickly ignited a fever pitch of paranoia and urgency. The policy of containment was no longer just about stopping the spread of communism. It was about managing a world where two titans could, at any moment, trigger an apocalypse. The arms race had officially transitioned from a sprint into a marathon of madness. The technological gap that had once provided a sense of security had vanished, replaced by a terrifying parity. The Soviet success signaled to the world that the nuclear genie could not be put back in the bottle. It was no longer a question of if the superpowers would clash, but how they would survive the collision. As the dust settled over the Kazakh desert, the stage was set for an even more terrifying evolution of weaponry. If fission had changed the world, the pursuit of something even more potent, the hydrogen bomb, was now inevitable. The era of the duel had begun. January 31, 1952, Enwetak Atoll, Marshall Islands. If the Soviet test in 1949 was a geopolitical earthquake, the detonation of the Ivy Mike device was a fundamental shift in the physics of human extinction. For years, the world had lived under the shadow of the fission bomb, a weapon that worked by splitting heavy, unstable atoms like uranium or plutonium. It was a violent, messy, and terrifying process, but it had a mathematical ceiling. There was a limit to how much energy could be squeezed from the splitting of a single nucleus. But as the mushroom cloud rose over the Pacific, the scientists in Los Alamos realized that humanity had just broken through that ceiling. They had moved from fission to fusion. The Ivy Mike test was not just a larger bomb, it was an entirely different species of destruction. It utilized the principle of thermonuclear fusion, the same process that powers the sun itself. In a fission bomb, you tear atoms apart. In a fusion bomb, you force them together. By using a primary fission explosion as a spark plug, scientists could create temperatures and pressures so intense that isotopes of hydrogen would fuse into helium, releasing an ocean of energy that made the Hiroshima blast look like a firecracker. The scale of the Ivy Mike explosion was incomprehensible. It released energy equivalent to 10.4 megatons of TNT, roughly 700 times more powerful than the bomb dropped on Hiroshima. The sheer magnitude of the blast transformed the concept of warfare. We were no longer talking about destroying a city. We were talking about erasing a province. We were talking about the ability to end civilization. In Washington, the atmosphere shifted from urgent to hysterical. The super, as the hydrogen bomb was colloquially known, became the new obsession of the American military-industrial complex. Led by figures like Edward Teller, the father of the hydrogen bomb, a faction of scientists and politicians argued that the only way to ensure American security was to build a weapon so massive, so devastating, that the very thought of using it would paralyze any aggressor. But this logic carried a dark, inherent paradox. To achieve security through the hydrogen bomb, the United States had to build an arsenal of weapons that no one could ever actually use. The pursuit of the ultimate deterrent was driving the nation toward a state of permanent readiness for a war that would leave no survivors to declare victory. The Soviet Union, sensing the American leap, did not retreat. They accelerated. The race was no longer about who had the bomb, but who could harness the power of the stars. The technological ladder was being climbed with terrifying speed, and each rung brought the world closer to a precipice. As the 1950s progressed, the hydrogen bomb ceased to be a theoretical possibility and became a standardized reality. The doctrine of war began to change. Military strategists were no longer planning for battles, maneuvers, or even tactical retreats. They were calculating megatonnage. They were weighing the survival of the species against the requirements of geopolitical dominance. The era of the fission duel had ended. The era of thermonuclear annihilation had begun. The sun had been brought down to Earth, and it was a sun that promised only darkness. Washington, D.C., 1953. The halls of the Pentagon and the Kremlin were no longer filled with the traditional maps of troop movements and supply lines. Instead, they were filled with something far more abstract and far more terrifying: the mathematics of survival. By the early 1950s, the technological leap from the fission bomb to the thermonuclear hydrogen bomb had fundamentally broken the logic of traditional warfare. In any previous era of human history, the goal of war was to achieve victory, to seize territory, to break an enemy's will, or to force a surrender. But as the megatonnage of nuclear arsenals began to climb, the very concept of victory began to dissolve into a mathematical impossibility. If one side launched a thermonuclear strike, the retaliation would not be a counterattack. It would be an apocalypse. This realization gave birth to a new, chilling strategic philosophy: the doctrine of deterrence. At its core, deterrence was built on a single, psychological premise: that the most effective way to win a war was to ensure that it could never be fought. It was a strategy of prevention through the threat of total destruction. For deterrence to work, an adversary had to believe two things. First, that you possess the capability to strike back with overwhelming force, and second, that you possess the political will to actually use that force. But as the United States and the Soviet Union raced to build larger arsenals, this doctrine evolved into its most extreme and nihilistic form: mutual assured destruction, or MAD. MAD was not merely a strategy, it was a terrifying equilibrium. It moved the world into a state of balance of terror. Under MAD, the survival of both the aggressor and the defender was tied to a single, shared destiny. It was a hostage situation on a planetary scale. If the United States launched its missiles, the Soviet Union's automated systems or submarine-based forces would launch theirs in return. The result would not be a winner and a loser, but a scorched, radioactive wasteland where neither side remained to claim the ashes. The logic was hauntingly simple. Because both sides were guaranteed to die, neither side could afford to start the fight. To make this guarantee, credible military planners realized they could not rely solely on land-based silos, which were vulnerable to a first strike. They needed a nuclear triad, a way to ensure that even if one part of the arsenal was wiped out, the ability to retaliate remained intact. This meant placing nuclear warheads on long-range bombers, in hardened underground silos, and most crucially, deep within the silent, unpredictable depths of the oceans via ballistic missile submarines. The goal was second strike capability. You had to be able to survive the end of the world just long enough to ensure your enemy met the same fate. This created a world of permanent, high-stakes tension. The doctrine of MAD turned the entire planet into a chessboard where a single mistake, a single miscalculation, or a single moment of madness could trigger the end of history. The peace of the era was not a peace of cooperation or understanding. It was a peace of pure, unadulterated fear. Humanity had entered a strange, dark era where the only thing keeping the world from burning was the collective realization that if the fire started, no one would be left to put it out. Kapustin Yar, Soviet Union, 1957. The thunderous roar of a rocket ascending into the stratosphere signaled more than just a technological milestone. It signaled the end of geography as a shield. For a decade, the primary delivery vehicle for nuclear terror had been the manned bomber. The logic of the early nuclear age was built around the cockpit and the flight path. To strike a target, a crew had to take off, navigate through enemy airspace, evade interceptors, and physically drop a payload. It was a slow, visible, and ultimately vulnerable process. Even with the advent of jet engines, a bomber was a massive, radar-detectable target that required hours of warning time to reach its destination. In the high-stakes game of deterrence, time was the most precious commodity, and bombers simply didn't provide enough of it. Then came the Intercontinental Ballistic Missile, or ICBM. Unlike a bomber, which crawls through the atmosphere, an ICBM is a creature of the vacuum. It is launched into a high, suborbital arc, leaving the dense air of the atmosphere behind, traveling at speeds that defy human comprehension. When a missile like the Soviet R-7 or the American Atlas was launched, it wasn't just a weapon. It was a fundamental rewrite of the rules of engagement. The revolution was defined by three terrifying new realities: speed, stealth, and inevitability. First, there was the collapse of reaction time. A bomber might take hours to cross an ocean. An ICBM could bridge continents in 30 minutes or less. This shrinking window of decision-making turned the concept of command and control into a frantic, automated nightmare. Generals and presidents no longer had hours to deliberate. They had minutes to decide whether a radar blip was a technical glitch or the beginning of the end of the world. Second, there was the problem of interception. How do you stop a warhead traveling at Mach 20? In the late 1950s and 60s, there was no defense. The missile was an unstoppable kinetic force. Once the engines burned out and the warhead began its descent, the target was essentially a ghost, waiting for an impact that no radar could prevent and no interceptor could catch. Finally, the ICBM changed the very nature of strategic geography. In the era of the bomber, distance provided a sense of security. Oceans were moats, mountain ranges were barriers, but the ICBM rendered the Earth flat. It didn't matter if your capital was tucked behind a mountain range or isolated by an ocean. If you were on the map, you were in range. The front lines of the Cold War were no longer at the borders of Europe or the edges of the Pacific. The front line was everywhere. As the 1960s progressed, the proliferation of these missiles turned the balance of terror into a race of pure mathematics. The focus shifted from how many planes a nation could fly to how many silos it could harden, how many re-entry vehicles it could fit onto a single rocket, and how quickly its computers could process a launch sequence. The ICBM revolution had completed the transition of nuclear warfare from a tactical military operation into a systemic, automated inevitability. The world was no longer protected by the distance between nations. It was held hostage by the sheer speed of the machines designed to destroy them. October 1962, Washington, D.C. The mathematical inevitability of the ICBM had reached a fever pitch, but the tension was about to move from the theoretical to the visceral. If the missiles had rendered the world flat, the sudden appearance of Soviet medium-range ballistic missiles in Cuba was about to make that world feel claustrophobic. For months, the Soviet Union had been engaged in a clandestine operation to fortify its presence in the Western Hemisphere. Under the cover of darkness and tropical storms, Soviet ships had been ferrying not just soldiers, but the very instruments of catastrophe. R-12 and R-14 missiles, capable of delivering nuclear warheads to almost any major American city within minutes. The secret was blown on October 14th, when a U.S. U-2 spy plane, soaring at the edge of space, captured high-resolution imagery of construction sites in the Cuban countryside. The intelligence was unequivocal. The Soviet Union wasn't just building defensive installations. They were placing a dagger at the throat of the United States. When President John F. Kennedy was briefed, the atmosphere in the Oval Office shifted from strategic competition to existential dread. This was no longer a game of long-range mathematics played across the Atlantic. This was a localized, immediate threat. The shrinking window of decision-making we discussed earlier had just slammed shut. For 13 days, the world held its breath. Kennedy established an ExComm, an executive committee of advisors, to weigh the impossible options. The military hawks pushed for a massive airstrike and a full-scale invasion of Cuba. They argued that anything less than total destruction of the missile sites would be a sign of weakness that would invite further Soviet aggression. But the president knew the terrifying logic of the era. An air strike on Cuba would almost certainly trigger a Soviet response in Berlin, which would escalate to a nuclear exchange between the superpowers. As the U.S. Navy implemented a quarantine, a naval blockade designed to stop further Soviet shipments, the world entered a state of paralyzed anticipation. Every Soviet ship approaching the line was a potential trigger for World War III. Every U-2 flight over Cuba was a gamble with life and death. The tension reached its zenith not in a boardroom, but in the dark, silent depths of the Atlantic. On October 27th, known as Black Saturday, a Soviet submarine, under pressure from U.S. depth charges, nearly launched a nuclear-tipped torpedo. In the halls of power, the red telephone did not yet exist. Communication was a slow, agonizing process of coded telegrams and public radio broadcasts. The crisis was finally broken through a fragile, back-channel diplomacy. A secret deal was struck. The Soviet Union would dismantle and remove the missiles from Cuba under UN supervision, and in exchange, The United States would publicly pledge never to invade the island. Behind the scenes, a second, more delicate component was added. The U.S. would quietly remove its own Jupiter missiles from Turkey. The crisis ended not with a bang, but with a profound, haunting silence. The world had stared into the abyss of total annihilation, and by a razor-thin margin of human willpower and diplomatic maneuvering, blinked. It was a sobering realization that in the nuclear age, victory was a hollow concept. There was only the narrow, terrifying possibility of survival. June 1963, Washington, D.C. The silence that followed the Cuban Missile Crisis was not a return to normalcy. It was the heavy, suffocating silence of a world that had realized how easily it could end. The lessons of October 1962 were etched into the minds of every leader in the Kremlin and the White House. They had learned that in the nuclear age, the greatest enemy was not necessarily the intent of the adversary, but the catastrophic failure of communication. During those 13 days of terror, the delay in communication had been a silent killer. To relay a message from Kennedy to Khrushchev, intelligence had to be translated, encrypted, transmitted via telegraph, decoded, decrypted, and then physically carried to the leaders. By the time a response arrived, the geopolitical landscape had often shifted, or worse, a misunderstanding had already triggered a kinetic response. In the era of ICBMs, where warheads could traverse continents in 30 minutes, the diplomatic lag was no longer a mere inconvenience, it was a death sentence. This realization birthed the era of brinkmanship. It was a high-stakes psychological game where both superpowers pushed each other to the absolute edge of conflict, testing resolve and red lines, gambling that the other side would blink first. But the mathematicians and strategists realized that if you play a game of brinkmanship without a way to signal a retreat, you eventually fall off the cliff. To prevent a war by accident, the two superpowers recognized the need for a direct, instantaneous link. This led to the formalization of the hotline, the legendary red telephone. Contrary to the popular cinematic myth of a bright red rotary phone sitting on a desk, the actual system established in 1963 was far more sophisticated and much more clinical. It was a dedicated, secure teleprinter link. It was a direct line of text, ensuring that complex diplomatic nuances were not lost in the crackle of a voice transmission or the heat of a heated argument. It was a direct bridge across the Iron Curtain, designed to bypass the slow, treacherous channels of traditional diplomacy. The hotline was a concession to reality. It was an admission that despite the ideological warfare, despite the race for supremacy, both sides shared a singular, terrifying interest, the preservation of the species. It was the first structural recognition of the rules of the game. It established that even at the height of hostility, there must be a way to say, wait, this was a mistake, do not respond. However, the creation of the hotline did not end the tension, it merely codified it. It turned the brink into a managed space. It allowed for a new kind of stability, a controlled instability, where leaders could engage in dangerous posturing, knowing they had a lifeline to pull them back from the void. As the 1960s progressed, the hotline became the ultimate safety valve in a world held together by the logic of mutual assured destruction. It was the thin, electronic thread that separated the era of managed rivalry from the era of accidental extinction. The world had learned that when you are playing a game where the loser dies, you must always keep the line open. July 1, 1968, New York City. If the hotline was a safety valve designed to prevent a sudden explosion, the world was now facing a much more slow-burning, systemic threat: the inevitable contagion of nuclear capability. Throughout the early 1960s, the nuclear club was expanding. The United States and the Soviet Union were the giants, but France, the United Kingdom, and China had already stepped onto the stage, claiming their own seats at the table of atomic power. The terrifying realization for diplomats was that this was only the beginning. If every nation felt the need to possess the ultimate deterrent to ensure its sovereignty, the world would soon become a crowded, chaotic, and hypervolatile landscape of dozens, perhaps hundreds, of nuclear-armed states. The math was simple and devastating. In a world of two superpowers, the logic of deterrence was a delicate, albeit terrifying, balance. In a world of 20 nuclear powers, the number of variables, the number of potential flashpoints, and the number of ways a single misunderstanding could trigger a global chain reaction became mathematically unmanageable. The risk was no longer just a clash of titans. It was the risk of a nuclear spark in a world filled with dry tinder. To combat this, the international community embarked on one of the most ambitious diplomatic undertakings in human history: the Treaty on the Non-Proliferation of Nuclear Weapons, or the NPT. The NPT was not a simple agreement. It was a grand, controversial, and deeply complex bargain. It was built upon three fundamental pillars, a tripod designed to hold up the weight of global security. The first pillar was non-proliferation. The established nuclear powers pledged they would never transfer nuclear weapons or technology to non-nuclear states. In exchange, the non-nuclear states pledged they would never seek, develop, or acquire them. It was a formal attempt to freeze the nuclear hierarchy in time. The second pillar was disarmament. This was the most contentious part of the deal. The non-nuclear nations demanded a guarantee. If they were to forgo the ultimate weapon, the powers that already possessed it had to commit to eventually dismantling their arsenals. It was a promise of a future without the bomb, a goal that remains a point of intense geopolitical friction to this day. The third pillar was the peaceful use of nuclear energy. The treaty recognized that nuclear science was not inherently evil. It held the promise of limitless power, medicine, and industry. It established a framework where nations could access nuclear technology for civilian purposes, provided they submitted to rigorous international inspections. This third pillar gave birth to the International Atomic Energy Agency, or the IAEA, the nuclear watchdog. For the first time, the world agreed that a nation's sovereignty over its own energy production would be subject to the eyes of the international community. When the NPT finally opened for signature, it was a moment of profound hope. It was a global consensus that the atom could be contained. Yet, even as the ink dried, the cracks were visible. The treaty created a two-tiered system: the haves and the have-nots. It institutionalized a global inequality that some argued was fundamentally unjust. The NPT was an attempt to build a dam against a rising tide of nuclear proliferation. It succeeded in slowing the spread, but it could never truly stop it. The world had agreed to a set of rules, but, as history would soon show, the pursuit of power often finds a way to bypass the law. September 26, 1983. Serpukhov 15, Soviet Union. While the world's diplomats were busy drafting treaties and building legal dams to contain the nuclear tide, A much more terrifying reality was unfolding behind the scenes. While we often think of nuclear war as a calculated decision made by leaders in high-level summits, the history of the late Cold War reveals a darker truth. We have survived not because our systems were perfect, but because of sheer, terrifying luck. The most chilling example occurred on a nondescript evening in the Soviet Union. An early warning satellite system reported that the United States had launched 5 Minuteman intercontinental ballistic missiles. The data was clear, the trajectory was certain, and the protocol was absolute. The Soviet leadership was seconds away from a retaliatory strike that would have ended civilization. But there was a glitch. A flaw in the satellite's software had mistaken the sun's reflection off high-altitude clouds for the heat signatures of missile engines. Had the duty officer followed the machine's command blindly, the world would have burned. It was the human element, a single officer named Stanislav Petrov, who intuited that a real first strike would involve hundreds of missiles, not 5, that prevented the apocalypse. He chose to trust his gut over the computer, a decision that remains one of the most significant moments in human history. But humans are fallible, and machines are unpredictable. In 1979, a similar ghost haunted the United States. At NORAD, a training exercise went catastrophically wrong when a technician accidentally loaded a real-world simulated warhead scenario into the computer system. For several agonizing minutes, the highest levels of the American military believed a massive Soviet strike was underway. The near miss was only averted when a supervisor realized the error, but the incident exposed a terrifying vulnerability. Our automated systems were capable of mistaking a drill for doomsday. The danger wasn't always a digital ghost, however. Sometimes it was a physical malfunction. In 1961, a B-52 bomber carrying 4 thermonuclear weapons experienced a mid-air malfunction over North Carolina. As the plane broke apart, the weapons actually released their firing mechanisms. Only because the physical arming triggers failed to complete their sequence did the bombs fall to the earth as inert metal rather than world-ending fire. These incidents reveal a haunting paradox at the heart of the nuclear age. We have spent decades building increasingly sophisticated, automated, and rapid response systems to ensure deterrence. We have built machines that can detect a launch in seconds and missiles that can strike in minutes. Yet, in our pursuit of perfection and speed, we have created a system where the margin for error has shrunk to almost zero. We are living in a state of managed chaos, where the survival of the species depends on a razor-thin margin between a technical glitch and a global catastrophe. The treaties of the NPT may govern the politics of the atom, but they cannot govern the laws of probability. As we look back at these near misses, we are forced to confront a chilling question. How many times have we already come too close to the edge without even knowing it? March 23, 1983, Washington, D.C. While the world held its breath over technical glitches and accidental near misses, the architects of superpower strategy were contemplating a shift that would fundamentally alter the logic of the Cold War. For decades, the terrifying stability of the nuclear age had rested on a single grim pillar: mutual assured destruction, or MAD. The logic was simple. If both sides possessed enough weapons to annihilate the other, neither would ever dare to strike first. Peace was maintained not by goodwill, but by the mathematical certainty of suicide. But in the early 1980s, President Ronald Reagan sought to break that deadlock. He envisioned a world where the threat of nuclear annihilation was no longer an inescapable shadow, but something that could be neutralized by technology. On this day, Reagan announced the Strategic Defense Initiative, or SDI. To the public, it was immediately dubbed Star Wars. The concept was as ambitious as it was science fiction: a sophisticated, space-based shield capable of detecting, tracking, and intercepting incoming Soviet missiles before they could reach their targets. Using a combination of high-powered lasers, particle beams, and advanced sensor arrays, the United States aimed to move from a posture of retaliation to one of defense. The implications were profound. If the United States could successfully build a shield, the entire doctrine of MAD would collapse. A nation that can defend itself is a nation that can strike without fear of a counter-response. To the Soviet leadership, SDI was not seen as a defensive measure, but as a revolutionary offensive tool, a way for the West to achieve nuclear hegemony by making the Soviet arsenal obsolete. The announcement sent shockwaves through the Kremlin. It ignited a new, high-tech dimension of the arms race. No longer was the competition merely about how many warheads one could pile into a silo or how fast a missile could fly. Now, the race was about computing power, satellite precision, and the mastery of directed energy. The battlefield was moving from the crust of the Earth into the vacuum of space. Critics, however, were vocal and skeptical. Many scientists argued that the technology required to intercept a ballistic missile in its terminal phase was decades, if not centuries, away from reality. They warned that SDI was an expensive fantasy that would only serve to destabilize the delicate balance of power. There was a deeper, more existential fear. If one side believed they could survive a nuclear strike, the temptation to launch a first strike might actually increase, turning a shield into a catalyst for war. Yet, regardless of its technical feasibility, SDI succeeded in its most potent, non-kinetic capacity. It forced the Soviet Union into an economic and technological corner. The sheer cost of trying to keep pace with an American technological leap threatened to bankrupt the already struggling Soviet economy. SDI changed the nature of the endgame. It shifted the focus from the quantity of destruction to the quality of innovation. It proved that in the nuclear age, the most powerful weapon wasn't always a bomb. Sometimes, it was the idea of a shield that could render the bomb useless. As the decade progressed, the Star Wars race would become a central pillar of the final, frantic sprint toward the end of the Cold War, proving that even in an era of certain destruction, humanity would always look to the stars for a way out. January 1, 1984, Omaha, Nebraska. As the high-stakes technological gamble of Star Wars unfolded in the heavens, the fundamental architecture of nuclear survival remained anchored to the ground, the sea, and the sky. While Reagan's SDI sought to build a shield, the military leadership of the superpowers remained obsessed with a different concept: survivability. They knew that a shield was a theoretical hope, but a strike was a physical certainty. To ensure that the doctrine of mutual assured destruction could never be circumvented by a sudden, overwhelming blow, the United States and the Soviet Union relied on a structural masterpiece of strategic planning known as the nuclear triad. The triad was not merely a collection of weapons. It was a philosophy of redundancy. The logic was chillingly pragmatic. If an enemy could find and destroy your missiles in their silos, or shoot down your planes on the runway, they might believe they could win a nuclear war. But if your retaliatory power was spread across three distinct, incomparable domains, the mathematical probability of a successful first strike dropped to near zero. The triad was designed to ensure that even if one leg was severed, the others would remain to deliver a terminal response. The first leg of this tripod was the land-based component, the intercontinental ballistic missiles, or ICBMs. These were the heavy hitters, housed in reinforced, hardened silos buried deep within the American Midwest or the vast Russian steppes. They were the most immediate and predictable arm of the triad. Because they were fixed in geography, they were vulnerable to precise targeting, but they possessed immense power and could be launched with devastating speed. They served as the ultimate deterrent, a visible, constant reminder of the cost of aggression. The second leg was the air-based component, the strategic bombers. Unlike the missiles in their silos, bombers provided a layer of flexibility and human judgment. They could be launched into the air as a show of force during a crisis, loitering in the skies to provide a mobile, unpredictable threat. While long-range missiles could bypass defenses, bombers could be rerouted, recalled, or used for precision strikes, offering a psychological dimension that a static missile could never achieve. But the most critical, most elusive leg was the sea-based component, the ballistic missile submarines, or SSBNs. Operating in the crushing silence of the deep ocean, these vessels were the ultimate insurance policy. A nuclear-armed submarine, hidden somewhere in the vast, trackless expanse of the Atlantic or Pacific, was nearly impossible to find and even harder to destroy. They were the survivable element of the triad. Even if a nation's cities were leveled and its silos were turned to glass, the silent watchers beneath the waves would emerge from the depths to ensure that the aggressor would not survive the night. The triad created a paradox of stability. By making a successful first strike impossible, it made the very idea of war unthinkable. It was a system built on the assumption of failure, the assumption that your own defenses might be breached, and use that failure to guarantee a counterstrike. In the shadow of the Cold War, the triad was the ultimate stalemate, a three-pronged guarantee that in a nuclear conflict there would be no victors, only survivors and the dead. April 26, 1986, Pripyat, Ukraine. For decades, the terrifying logic of the nuclear age had been defined by the calculated movements of superpowers, a chess match played with missiles, bombers, and submarines. The fear was existential, but it was controlled. It was a fear of a deliberate human decision to end the world. But in the early hours of a spring morning in the Soviet Union, that controlled fear was shattered by something far more unpredictable: a mistake. When the reactor core at the Chernobyl nuclear power plant exploded, it did more than release a plume of radioactive isotopes into the atmosphere. It breached the fundamental psychological barrier that had separated the military atom from the civilian atom. Until this moment, the public had largely viewed nuclear technology through two distinct lenses: the terrifying weapon of war and the miraculous promise of limitless, clean energy. Chernobyl collapsed those two worlds into one. As the invisible cloud of radiation drifted across the borders of Europe, the world realized that a nuclear catastrophe did not require a declaration of war or a command from a general. It could be triggered by a faulty valve, a tired technician, or a flawed design. The shadow cast by Chernobyl was the realization that the atom was not just a weapon held by states. It was a volatile force that could become an enemy of humanity through sheer human error. The immediate aftermath was a masterclass in systemic failure. The Soviet attempt to shroud the disaster in secrecy only deepened the global sense of vulnerability. When the truth finally emerged, it fundamentally altered the public psyche. The atomic age had promised a utopia of electricity. Instead, it had delivered a landscape of exclusion zones and poisoned soil. In the West, this ignited a fierce, grassroots anti-nuclear movement that moved beyond the political fringes and into the mainstream. The fear was no longer just about the big bomb. It was about the power plant in your backyard, the reactor in your province, the invisible threat that could render entire nations uninhabitable without a single shot being fired. This shift in consciousness had profound geopolitical consequences. It eroded the perceived infallibility of the Soviet state, exposing a level of incompetence and systemic decay that would eventually contribute to the collapse of the USSR. But even more significantly, it changed the way the world viewed risk. The era of technological optimism, the unquestioning belief that science could solve all human problems, began to give way to an era of profound skepticism. Chernobyl proved that while the nuclear triad could manage the risks of war, it was utterly unequipped to manage the risks of complexity. The math of deterrence worked for missiles, but it did not work for radiation. As we moved toward the end of the Cold War, the shadow of the reactor loomed just as large as the shadow of the warhead. The world learned a bitter lesson. In the nuclear age, the most dangerous trigger is not always a finger on a launch button, but the simple, devastating possibility of a mistake. December 25, 1991, Moscow, Russia. As the hammer and sickle was lowered from the Kremlin for the final time, a new and terrifying geopolitical reality began to set in. For 45 years, the world had lived under a predictable, if harrowing, bipolarity. The nuclear math was simple: two superpowers, two arsenals, and a clear chain of command. But as the Soviet Union disintegrated into 15 independent states, that mathematical certainty vanished, replaced by a chaotic, fragmented landscape that threatened to undo decades of diplomatic stability. The collapse did not just redraw the maps of Eastern Europe, it shattered the control mechanisms of the world's largest nuclear arsenal. Suddenly, the vast, sprawling infrastructure of the Soviet nuclear complex, thousands of warheads, highly enriched uranium and sophisticated delivery systems, was no longer under the centralized authority of a single, cohesive government in Moscow. Instead, it was scattered across newly sovereign nations like Ukraine, Kazakhstan, and Belarus. The world watched with bated breath, gripped by a phenomenon that would become known as the loose nukes fear. The central question was no longer whether a superpower would launch a strike, but whether a rogue general, a corrupt official, or a desperate criminal could seize a weapon in the vacuum of a collapsing state. The logistics of nuclear security are immense. Maintaining a nuclear arsenal requires more than just the warheads themselves. It requires a stable economy to pay technicians, secure borders to prevent smuggling, and a functional command and control architecture to ensure that the button is only pressed by authorized hands. As the Soviet ruble plummeted and the central government lost its grip on its provinces, the very foundations of nuclear security began to crumble. Intelligence agencies across the West entered a state of high alert. The nightmare scenario was not a nuclear war between nations, but the proliferation of nuclear material to non-state actors. The fear was that a dirty bomb, a conventional explosive laced with radioactive isotopes, could be constructed by a terrorist organization using materials stolen from a poorly guarded Soviet warehouse. The invisible, highly enriched uranium that once fueled the Soviet war machine could now become a portable instrument of mass terror, capable of turning a city center into a radioactive wasteland. This period of profound instability forced a frantic, high-stakes diplomatic scramble. The United States and the international community launched initiatives like the Nunn-Lugar Cooperative Threat Reduction Program. This was a historic, unprecedented attempt to fund and facilitate the dismantling of nuclear weapons and the securing of materials in the former Soviet republics. It was a race against time, an effort to stabilize the wreckage of a fallen empire before the pieces could be sold on the black market. The collapse of the USSR proved that the greatest danger in the nuclear age is not always the presence of weapons, but the absence of order. We had spent decades preparing for a clash of titans, a structured conflict between organized states. We were fundamentally unprepared for the era of fragmentation. The transition from the Cold War to the post-Soviet era revealed a chilling new truth. When a nuclear power dies, its weapons do not die with it. They become orphans of history, drifting in the shadows of a changing world, waiting to see if they will be dismantled or lost. July 31, 1991, Geneva, Switzerland. While the world's intelligence agencies scrambled to secure the physical remnants of the Soviet Empire, a different kind of battle was being fought in the quiet, sterile halls of diplomatic summits. If the collapse of the USSR represented the chaos of fragmentation, the era that followed was defined by a desperate, calculated attempt to find order through reduction. The era of more was over. The era of less had begun. For decades, the logic of the arms race had been additive. Every breakthrough in missile technology or warhead miniaturization was met by a counter-breakthrough from the opponent. But as the smoke cleared from the Cold War, a profound realization took hold among the architects of global security. The stockpiles had reached a point of diminishing returns. The sheer volume of nuclear material was no longer a deterrent. It was a liability. A massive, unstable mountain of plutonium and uranium that increased the risk of accidental launch, theft, or catastrophic mismanagement. The primary instrument of this new era was the Strategic Arms Reduction Treaty, better known as START. This was not merely a pause in the arms race, but a fundamental reversal of it. Unlike previous treaties that merely sought to cap the growth of arsenals, START demanded the actual, physical destruction of weapons. The negotiations were grueling. Under the START-I agreement, the United States and the newly formed Russian Federation committed to deep, verifiable cuts in their strategic nuclear forces. This was a monumental shift in international law. For the first time, the superpowers weren't just agreeing on how many missiles they could have. They were agreeing on how many they had to destroy. The process of dismantling these warheads was a gargantuan industrial undertaking. It was a grim, high-tech form of alchemy. At specialized facilities in both the American Midwest and the Russian interior, technicians worked in heavy protective gear to disassemble the most complex machines ever built by man. The high explosives were removed, the firing mechanisms neutralized, and the delicate physics packages were carefully deconstructed. But the most significant challenge was the fuel, the fissile material. The highly enriched uranium and plutonium that once promised global dominance now posed a terrifying environmental and security risk. The dismantling process required a delicate dance of chemistry and logistics, converting weapons-grade plutonium into stable oxides, or vitrifying radioactive waste into glass to prevent it from leaching into the groundwater. This era of disarmament was fueled by a rare moment of geopolitical alignment. There was a shared understanding that the stability of the Cold War was a fragile illusion, and that true security could only be found in the reduction of the threat. The START treaties provided a framework for transparency, allowing inspectors to cross borders and verify that the destruction was real. It turned the once secretive silos of the superpowers into sites of supervised demolition. Yet, even as the numbers on the ledgers began to drop, the underlying tension never truly vanished. The dismantling of the old warheads was a triumph of diplomacy, but it was also a race against the ticking clock of political instability. We were learning how to unmake the very things we had spent half a century learning how to build. The disarmament era proved that while building a weapon of mass destruction is an act of scientific will, destroying one is an act of political courage. October 3, 1994, Pyongyang, North Korea. While the titans of the old world were busy dismantling their arsenals and signing treaties of reduction, a shadow was lengthening in the east. The diplomatic optimism that had characterized the early 1990s, the belief that the era of proliferation was closing, was about to collide with a harsh, localized reality. The order the world had fought so hard to establish through the Non-Proliferation Treaty was being fundamentally challenged, not by a superpower seeking dominance, but by a smaller, isolated state seeking survival. For the Democratic People's Republic of Korea, the collapse of the Soviet Union was not a moment of democratic transition, but an existential crisis. The loss of their primary patron meant the loss of subsidized fuel, food, and most critically, the technical expertise that had sustained their regime. In the vacuum left by the Cold War, Pyongyang turned inward, accelerating a clandestine nuclear program that would become the ultimate test of the international non-proliferation regime. The world watched with growing alarm as North Korea began to play a dangerous game of brinkmanship. In the mid-90s, the crisis peaked when the International Atomic Energy Agency discovered evidence of undeclared plutonium production at the Yongbyon nuclear facility. The North Korean question was no longer a theoretical concern for intelligence analysts. It was a live geopolitical firestorm. The resulting 1994 agreed framework was a desperate attempt to freeze the clock, a deal where North Korea would freeze its plutonium program in exchange for heavy fuel oil and commitments to dismantle its nuclear infrastructure. But the clock did not stop, it merely reset. By the early 2000s, the framework had crumbled. North Korea's withdrawal from the Non-Proliferation Treaty marked a terrifying milestone in nuclear history, the emergence of a non-treaty nuclear power. Unlike the US or the USSR, which operated within a recognized, albeit tense, legal framework of deterrence, North Korea was stepping outside the law entirely. They were not seeking to balance a superpower. They were seeking a survival insurance policy that would make the cost of regime change prohibitively high. In 2006, the world heard a sound it had feared since the Trinity test, the roar of a North Korean underground nuclear explosion. It was a watershed moment. It proved that the safeguards of the NPT were not impenetrable. It demonstrated that a determined state could bypass the global consensus through deception, domestic scientific mobilization, and sheer political will. This was the birth of a new, more unpredictable era of proliferation. The North Korean question revealed a terrifying flaw in the global security architecture. The system was designed to manage the behavior of giants, but it was ill-equipped to handle the defiance of the outliers. As Pyongyang moved from fission to advanced delivery systems, the geopolitical calculus changed. The threat was no longer just about a massive exchange of missiles between two poles. It was about the unpredictable actions of a state that felt it had nothing left to lose. The era of controlled disarmament was being eclipsed by an era of fragmented, rogue proliferation, where the rules of the game were being rewritten by those who refused to play by them. 2002. Tehran, Iran. If North Korea represented the defiance of the outlier, the situation in Iran represented something far more complex: a deep, systemic entanglement of scientific aspiration, regional hegemony, and the fragile architecture of international law. Unlike the isolated, hermit state aggression of Pyongyang, the Iranian nuclear issue emerged not from a sudden withdrawal from the world, but from a long-standing, opaque, and deeply suspicious dance within it. The world's attention shifted toward the Persian Gulf as intelligence reports began to surface, suggesting that Iran's nuclear ambitions went far beyond the stated goal of peaceful energy production. For decades, the Iranian government had maintained that its nuclear program was a matter of national sovereignty, a right granted under the Non-Proliferation Treaty to harness the atom for electricity and medicine. But to the West, and more acutely to Israel, the enrichment of uranium and the development of centrifuge technology looked less like a power plant and more like a path to a weapon. This was not merely a technical dispute, it was a geopolitical earthquake. The Middle East is a region defined by razor-thin margins of power and ancient, simmering rivalries. In this landscape, the introduction of a nuclear-armed Iran would not just change the balance of power, it would fundamentally rewrite the rules of survival for every state in the vicinity. The dilemma created a profound strategic nightmare. If the international community allowed Iran to proceed, they risked a regional arms race. Saudi Arabia, Egypt, and Turkey might feel compelled to follow suit, leading to a cascade effect, where the Middle East becomes a patchwork of nuclear-armed states, making the doctrine of deterrence nearly impossible to manage. Conversely, if the world moved to forcefully stop Iran, they risked a major conventional war that could destabilize global energy markets and ignite a sectarian conflagration. The struggle moved from the laboratories to the halls of the United Nations. The mid-2000s saw a frantic period of diplomacy, characterized by the P5+1 negotiations, the 5 permanent members of the Security Council plus Germany. It was a high-stakes game of shadows and sanctions. The West utilized economic warfare, freezing Iranian assets and tightening the noose around its economy, hoping to force Tehran to the negotiating table. The tension reached a fever pitch with the discovery of undeclared facilities at sites like Natanz and Fordo. These were not just laboratories. They were symbols of a regime that seemed to be playing a dual game, participating in the global order while simultaneously building the tools to defy it. The suspicion was that Iran was seeking breakout capability, the ability to produce enough weapons-grade material to assemble a bomb within a very short window of time, effectively holding the world hostage to its timeline. This brings us to the heart of the Iran dilemma, the intersection of legitimate scientific pursuit and the terrifying potential for nuclear blackmail. It highlighted a terrifying reality of the 21st century. The NPT, once thought to be the bedrock of global security, could be used as a shield by a state to advance its capabilities under the guise of civilian progress. As the world moved into the 2010s, the Iran question became the ultimate litmus test for whether diplomacy could actually contain the atom, or if the only way to stop a nuclear state was through the very violence the treaties were designed to prevent. 2001, New York City. As the world's eyes were fixed on the shifting sands of the Middle East and the diplomatic chess matches of Tehran and Pyongyang, a far more intimate and unpredictable terror began to haunt the corridors of global intelligence. For much of the 20th century, the nuclear threat was a predictable, if terrifying, game played by giants. It was a game of states, of borders, of clear command structures, and of the cold logic of mutually assured destruction. But as the new millennium dawned, a new shadow emerged, one that did not respect borders, did not fear retaliation, and could not be deterred by the threat of a counterstrike. The rise of non-state actors, terrorist organizations, and radicalized insurgent groups introduced a variable that the architects of the Cold War had never fully accounted for: the irrational actor. The nightmare scenario was no longer just a missile silo in a distant land. It was the possibility of a dirty bomb. Unlike a thermonuclear device, which relies on a complex high-tech chain reaction to create a massive explosion, a radiological dispersal device, or RDD, is a much simpler, more insidious weapon. It is a conventional explosive, such as dynamite or TNT, laced with radioactive isotopes like cesium-137 or cobalt-60. The goal of a dirty bomb is not mass instantaneous death through blast pressure. Rather, it is the weaponization of fear and the paralysis of infrastructure. A single detonation in the heart of a metropolis like London, Tokyo, or New York would not level skyscrapers, but it would coat entire city blocks in a fine, invisible, and lethal dust. The economic fallout would be catastrophic. The cost of decontamination, the mass evacuation of millions, and the sheer psychological trauma would render entire urban centers uninhabitable for years. It is a weapon of chaos, designed to turn the very air we breathe into a source of dread. This fear was not merely academic. Following the collapse of the Soviet Union, the international community faced the terrifying specter of loose nukes. The possibility that highly enriched uranium or plutonium could be stolen from poorly guarded stockpiles or diverted from crumbling research facilities. The intelligence community began to realize that the nuclear umbrella provided by superpowers offered little protection against a decentralized network of extremists who viewed the destruction of the existing world order as a divine or political necessity. The security paradigm underwent a radical shift. The focus moved from strategic stability between nations to nuclear security within borders. The global initiative to combat nuclear terrorism was born, and the hunt for precursor materials, the chemicals and isotopes used in nuclear medicine and industry, became a frontline in the war on terror. Every hospital, every industrial site, and every scrap yard became a potential point of failure in the global shield. We entered an era where the threat was no longer just a matter of high-level geopolitics, but of granular, street-level vigilance. The question was no longer just, will a nation-state launch a missile? But rather, can we stop a small cell of individuals from turning a piece of medical equipment into a tool of mass panic? In this new landscape, the atom had been democratized in the worst possible way, moving from the controlled laboratories of the superstates into the unpredictable, dark corners of a fractured world. 2010, Washington, D.C. As the fear of decentralized terror gripped the public imagination, the high-stakes game of traditional statecraft did not disappear. It simply evolved. While intelligence agencies were hunting for illicit shipments of isotopes in shipping containers, a much more sophisticated, silent war was being waged in the shadows of embassies and the encrypted servers of national security agencies. This was the intelligence war, a complex, multi-layered struggle where the weapons were not warheads, but information, deception, and the delicate art of diplomacy. In the post-Cold War era, the goal of intelligence shifted from predicting a massive, singular strike to the granular task of proliferation monitoring. The objective was to map the invisible networks of nuclear procurement. Intelligence agencies began focusing on the dual-use problem, the reality that the same centrifuge technology used to enrich medical isotopes could, with a slight adjustment, produce weapons-grade uranium. Spies were no longer just looking for missile silos. They were looking for procurement agents in shell companies, subtle discrepancies in scientific journals, and the movement of specialized high-strength steel across borders. The intelligence gathered in these shadows became the primary fuel for the diplomatic fires of the 21st century. Every piece of intercepted communication, every satellite image of a construction site in the Iranian desert, and every human intelligence report from a rogue scientist became a bargaining chip at the negotiating table. We saw this play out in the grueling cycles of the Joint Comprehensive Plan of Action, or the Iran nuclear deal. Diplomacy here was not a matter of goodwill, but a calculated response to intelligence data. The question was always, how much do we actually know? How much of a program is for civilian energy, and how much is a breakout capability hidden behind a veil of plausible deniability? The tension between intelligence certainty and diplomatic compromise became the defining friction of modern nuclear policy. If the intelligence was too weak, the world faced the risk of a preemptive strike. If it was too aggressive, it risked triggering the very war it sought to prevent. But as diplomacy sought to build walls of regulation, the intelligence war also moved into the digital realm. The emergence of cyber warfare introduced a terrifying new dimension to nuclear stability. The discovery of the Stuxnet worm, a sophisticated piece of malware designed to physically destroy Iranian nuclear centrifuges, proved that a nation's most guarded physical assets could be sabotaged without a single soldier crossing a border. This changed the calculus of deterrence forever. In the past, a nation could rely on the physical security of its facilities. Now, the digital perimeter became as vital as the concrete walls of a reactor. The intelligence war became a race between those trying to hide their nuclear ambitions behind layers of code and those trying to pierce those layers to expose the truth. In this era, the line between knowing and acting became razor-thin. The interplay of spying and diplomacy created a world where the most consequential decisions were often made based on what was not seen, or what was implied by a whispered report in a secure briefing room. The atom was no longer just a matter of physics. It had become a matter of perception, a high-stakes game of shadows where the truth was the most precious and most dangerous commodity of all. 2015, Colorado Springs, Colorado. As the intelligence wars of the early millennium grew more complex, the physical arsenals of the world's nuclear powers faced a different, more existential crisis: obsolescence. For decades, the global nuclear posture had been defined by the sheer volume of warheads, massive, aging stockpiles built during the frantic height of the Cold War. These were the city killers, weapons designed for a world of total war and blunt force. But as the geopolitical landscape shifted toward regional conflicts and asymmetric threats, The sheer weight of these old arsenals became a liability. They were expensive to maintain, difficult to secure, and increasingly ill-suited for the surgical precision required by 21st century doctrine. The era of more was giving way to the era of better. This period marked a profound technological pivot known as the life extension programs and the transition to modernized arsenals. The goal was no longer to build more bombs, but to transform the existing ones into high-tech, highly reliable instruments of precision. This wasn't merely a matter of refurbishing old hardware. It was a fundamental reimagining of the nuclear delivery system. The modernization movement focused on three critical pillars: reliability, accuracy, and survivability. First, there was the challenge of aging components. After decades of sitting in silos or submerged in the depths of the ocean, the materials inside a warhead, the electronics, the firing mechanisms, even the chemical compositions of the explosives, began to degrade. Engineers were tasked with the monumental job of replacing these aging parts with modern, digital equivalents, without altering the fundamental physics that ensured the weapon would function exactly as intended. Second, the focus shifted toward extreme accuracy. In the Cold War, if a missile was off by a few hundred meters, it didn't matter. The blast radius of a multi-megaton hydrogen bomb would still erase everything in its path. But in a modern era characterized by limited nuclear options, and the need to strike hardened, deeply buried command bunkers, precision became the new priority. The development of advanced guidance systems, utilizing GPS and sophisticated inertial navigation, meant that a modern warhead could strike a target with a degree of surgical accuracy that would have seemed like science fiction to the architects of the Manhattan Project. Third, and perhaps most importantly, was the modernization of the delivery platforms. The aging fleets of bombers and the massive, lumbering ICBMs were being supplemented or replaced by more stealthy and agile systems. The focus turned to low observable technologies, missiles designed to evade increasingly sophisticated radar and missile defense shields. The goal was to ensure that the deterrence part of mutual assured destruction remained credible. If a nation believed its second strike capability could be neutralized by an enemy's defensive shield, the entire logic of peace through strength would collapse. This transition represents a quiet but radical evolution. We moved from the era of the sledgehammer, a weapon of indiscriminate, catastrophic scale, to the era of the scalpel. While this shift was framed as a way to make nuclear weapons more manageable and controllable, it also introduced a new layer of terrifying complexity. As warheads became more precise, the margin for error in decision-making shrank, and the threshold for what might constitute a usable nuclear weapon began to blur. The arsenal was no longer just a collection of dormant giants. It had become a finely tuned, high-tech machine, waiting in the shadows of a digital age. 2024, Moscow, Russia. If the modernization of the nuclear arsenal was the refinement of the scalpel, then the emergence of hypersonic technology represents the erasure of the surgeon's steady hand. We are entering a new, even more volatile chapter of the nuclear age, one where the fundamental physics of time and distance are being rewritten. For the better part of 70 years, the stability of the nuclear order relied on a predictable, if terrifying, mathematical certainty: the flight time of an intercontinental ballistic missile. When an ICBM is launched from a silo in the Midwest or a submarine in the Pacific, it follows a high, parabolic arc, a predictable trajectory that can be tracked by space-based infrared sensors and long-range radar systems. This arc provides a window of warning. It provides the precious minutes, sometimes as little as 15 to 30, required for leaders to verify the launch, communicate with adversaries, and decide whether to launch a retaliatory strike or stand down. This window, however agonizingly brief, was the buffer that prevented a false alarm from escalating into a global holocaust. Hypersonic weapons have just shattered that buffer. Unlike traditional ballistic missiles, which fly up into the vacuum of space before descending on a fixed path, hypersonic glide vehicles, or HGVs, operate in a different realm. They fly at speeds exceeding Mach 5, but more importantly, they fly in the near-space corridor, too low to be easily tracked by early warning satellites designed for high-altitude ballistic arcs, and too high to be engaged by conventional surface-to-air missile defenses. But speed is not their only weapon, it is their maneuverability. A traditional missile is like a thrown stone. Once it leaves the hand, its path is largely set. A hypersonic missile is like a guided hawk. It can skip along the upper atmosphere, changing direction and altitude mid-flight to evade detection and circumvent defensive shields. This capability fundamentally breaks the logic of early warning. In the Cold War, if a radar pinged, you knew where the threat was coming from and roughly when it would arrive. In the hypersonic era, the threat can appear on the radar horizon with almost no warning, and by the time the system confirms the trajectory, the missile may already be seconds from impact. We are no longer looking at a 30-minute warning window. We are looking at a 5-minute window, or perhaps 3. This compression of time creates a phenomenon known as launch-on warning pressure. When the time between detection and impact shrinks to the point where a leader cannot distinguish between a technical glitch and a genuine decapitation strike, the incentive to use them or lose them becomes overwhelming. The hesitation that once allowed for diplomacy is being squeezed out by the sheer velocity of the hardware. As the United States, Russia, and China race to master this technology, the strategic landscape is shifting from a game of chess to a game of high-speed reflexes. We have moved beyond the era of the scalpel. We have entered an era of hypervelocity, where the machines move faster than the human capacity to think, leaving the fate of civilization to hang on the split-second decisions of an increasingly stressed and compressed command structure. The buffer is gone. The clock is accelerating. And the silence of the deterrent is being replaced by the scream of something moving faster than thought. 2024, Silicon Valley, California. If hypersonic weapons have stolen our time, then artificial intelligence threatens to steal our agency. For decades, the human in the loop has been the ultimate fail-safe of the nuclear age. From the harrowing moments when Stanislav Petrov stared at a flickering radar screen in 1983 and chose to trust his intuition over a computer error, to the high-stakes deliberations in the Situation Room, the final line of defense against accidental annihilation has been human judgment. We have relied on the capacity for doubt, the ability to question a censor, and the moral weight of a conscience. But as the window of decision-making shrinks from 30 minutes to mere seconds, a terrifying question begins to emerge in the halls of defense ministries. Can a human being actually keep up? We are witnessing the birth of algorithmic warfare. In this new paradigm, the integration of AI into nuclear command, control, and communications, known as NC3, is no longer a theoretical exercise. It is a strategic necessity. The logic is seductive. An AI can process petabytes of sensor data from satellites, underwater hydrophones, and cyber monitoring systems simultaneously. It can identify patterns of mobilization, detect the subtle signatures of a hypersonic launch, and cross-reference them against geopolitical intelligence in milliseconds. An algorithm does not panic. It does not suffer from fatigue. It does not hesitate. In a world of hypervelocity weapons, proponents argue that delegating certain analytical functions to AI is the only way to maintain a credible deterrent. If your adversary is using machine learning to optimize their strike windows, you cannot afford to rely on a human who needs 10 minutes to drink a cup of coffee and read a briefing. But this efficiency comes with a Faustian bargain. When we move from AI-assisted decision-making to AI-driven response, we risk entering the era of flash wars, unintended escalations triggered by interacting algorithms. Imagine two opposing nuclear command systems, both designed to react at machine speed. If one AI misinterprets a solar flare, a cyber attack, or a routine military exercise as a precursor to a strike, it may trigger a defensive posture. The opposing AI, sensing this movement, responds in kind. In a matter of seconds, a cycle of automated escalation could spiral toward a nuclear exchange before a single human being is even notified that a crisis has begun. This is the black box problem of nuclear stability. Deep learning models are notoriously opaque. Even their creators often cannot explain exactly why an AI reached a specific conclusion. If an algorithm recommends a retaliatory strike, how can a commander verify its reasoning in the 3 minutes they have left to live? To trust the machine is to embrace a logic that is fundamentally inhuman. We are effectively outsourcing our survival to mathematical weights and biases. We are trading the messy, slow, but ultimately empathetic process of human diplomacy for the cold, optimized, and lightning-fast certainty of code. As we integrate these silicon brains into our most lethal arsenals, we must confront the ultimate paradox of the modern age. In our desperate attempt to use technology to secure our survival, we may be creating a system so fast and so complex that it removes our ability to choose life at all. The finger on the button is being replaced by a line of code, and once that code begins to run, there is no way to pull it back. 2024, Fort Meade, Maryland. If the integration of AI threatens to strip away our agency, then the emergence of sophisticated cyber warfare threatens to strip away our reality. For the entirety of the nuclear age, the greatest fear was a breakdown in communication, a severed telephone line, or a blinded satellite that would leave a superpower in a state of paralyzed uncertainty. But in the digital era, the threat is no longer just the absence of information. It is the presence of false information. It is the possibility that the very systems designed to protect us could be turned into the instruments of our destruction. We are entering an era where the battlefield is not just physical but virtual. The command and control systems, the NC3 architecture, that hold the keys to our nuclear arsenals are, at their core, incredibly complex networks of software, hardware, and data links. They are the digital nervous system of the state, and like any nervous system, they are vulnerable to infection. The nightmare scenario for modern strategists is a cyber-induced nuclear escalation. This is not a Hollywood trope of a hacker simply pressing a button. It is something far more insidious. It is the subtle, surgical manipulation of the data that informs our decision-making. Imagine a sophisticated state-sponsored actor infiltrating the digital infrastructure of a nuclear power. They don't need to launch a missile. They only need to make it look like a missile has been launched. By injecting malicious code into early warning sensors, they could create ghost signatures on a radar screen, simulated incoming warheads that appear entirely legitimate. In the high-pressure environment of a nuclear crisis, where every second is a currency of survival, the distinction between a digital hallucination and a physical reality becomes impossibly thin. If an adversary can spoof our sensors, they can force us into a use it or lose it dilemma. They can manipulate our perception of the truth so effectively that we are driven to launch a retaliatory strike against a threat that never existed. Furthermore, there is the terrifying prospect of command hijacking. What happens if a cyber attack doesn't just provide false data, but actually gains control over the authorization protocols themselves? If the digital handshake required to verify a launch command can be forged or bypassed, the most sacred safeguard of the modern age, the integrity of the command chain, is shattered. We are no longer just defending borders or airspaces. We are defending the integrity of the bit and the byte. We are fighting a war of shadows where the weapon is a string of code and the casualty is the truth. This creates a profound instability in the doctrine of deterrence. Deterrence relies on the rational actor theory, the belief that both sides can clearly communicate their intentions and read each other's moves. But cyber warfare introduces a layer of radical unpredictability. When a nation can no longer trust its own digital eyes, the very foundation of strategic stability begins to crumble. As we weave our nuclear command structures ever tighter into the global web of digital connectivity, we are building a house of cards in a digital hurricane. We are creating a world where a single line of malicious code, written in a basement halfway across the globe, could inadvertently trigger the end of civilization. In the nuclear age, the greatest threat may no longer be the bomb itself, but the invisible, untraceable ghost in the machine. 2024, Beijing, China. While the digital shadows of cyber warfare threaten to destabilize the systems we have built, a much more visible and structural shift is occurring in the geopolitical landscape. For nearly 8 decades, the logic of nuclear existence was governed by a simple, brutal mathematical equation: 2 players, 2 arsenals, and a singular, terrifying equilibrium. This was the era of the US-Russia duopoly, a bipolar world where the rules of engagement, the treaties of disarmament, and the very concept of mutually assured destruction were negotiated in a binary dialogue between Washington and Moscow. But that era of predictable tension is dead. As the 21st century progresses, the geometry of global power is shifting from a straight line to a complex, multidimensional web. The rise of China as a peer competitor is not merely a change in the balance of power. It is a fundamental disruption of the nuclear status quo. For decades, China maintained a minimal deterrent, a modest, qualitative arsenal designed to ensure that any nuclear strike against the mainland would be met with unacceptable costs. But that restraint has evaporated. Today, we are witnessing an unprecedented expansion of the Chinese nuclear triad. From the construction of hundreds of new missile silos in the western deserts to the deployment of advanced, road-mobile ICBMs and stealthy, nuclear-powered submarines, Beijing is racing to transform its arsenal from a defensive shield into a global sword. This is not a slow evolution. It is a rapid, systematic buildup designed to ensure that in any future conflict, China does not merely survive, but can project power across the entire Pacific and beyond. This transition from a bipolar to a multipolar nuclear order shatters the old calculus of deterrence. In the Cold War, if the United States and the Soviet Union understood each other's red lines, they could avoid the brink. But in a tripolar world, the math becomes exponentially more volatile. Deterrence is no longer a game of two-player chess. It is a chaotic, three-way poker game where every move by one player can trigger a cascade of reactions from the others. If the US and Russia engage in an arms race to modernize their aging stockpiles, how does China respond? If China expands its silos to counter a perceived threat, does that force Washington to pivot resources away from Europe and toward the Pacific, inadvertently creating a vacuum that Moscow might exploit? In this new landscape, strategic stability is a moving target. The old treaties, the START agreements and the INF Treaty, were designed for a world of two. They are increasingly ill-equipped to manage a world where a third, massive actor can unilaterally alter the stakes. The danger of this new multipolarity is the triangular instability. It creates a scenario where no two powers can feel truly secure without accounting for the third. A move to strengthen a missile defense shield in California might be seen by Moscow as a threat to its deterrent, but by Beijing as a challenge to its regional hegemony. We are moving away from the era of managed rivalry and into an era of unmanaged competition. The predictable, if terrifying, stability of the Cold War has been replaced by a fragmented, high-stakes scramble for nuclear parity. As the pillars of the old order crumble, we find ourselves in a world where the rules are being rewritten in real time, and the margin for error is shrinking with every new silo that rises from the earth. 2024, Geneva, Switzerland. For decades, the halls of international diplomacy have been the thin line of defense between civilization and annihilation. Here, in the quiet corridors of the United Nations and the various arms control summits, the world attempted to impose a framework of restraint upon the chaos of human ambition. We built a legal architecture, a complex web of treaties like the NPT, the SALT agreements, and the INF Treaty, designed to act as a global thermostat, cooling the fever of nuclear competition. But that architecture is not just cracking, it is being systematically dismantled. We are currently witnessing the great unraveling, the era of managed disarmament, where the superpowers sat across from one another to count warheads and verify silos, is being replaced by an era of unilateral withdrawal. The treaties that once provided the rules of the road are being treated less like sacred commitments and more like obsolete relics of a bygone age. The first tremor in this collapse came with the death of the INF Treaty, the Intermediate-Range Nuclear Forces Treaty. For 30 years, this agreement had prevented a massive buildup of missiles in Europe, acting as a buffer against a localized nuclear conflict. Its dissolution has reopened a landscape of tactical uncertainty, turning the European continent back into a potential chessboard for short-range, high-speed nuclear deployment. Then came the suspension of New START, the last remaining pillar of the bilateral arms control regime between the United States and Russia. When the ability to conduct on-site inspections and share strategic data vanished, the eyes of the world were effectively blinded. Without verification, suspicion becomes the default setting. Without transparency, every military exercise, every new silo, and every technological breakthrough is viewed through the lens of maximum paranoia. We have moved from a period of trust but verify to a period of assume the worst. But why is this happening now? Why is the global community allowing the guardrails to be stripped away? The answer lies in the fundamental shift in how nations perceive security in a multipolar world. In the 20th century, treaties were a way to manage a predictable rivalry. In the 21st century, they are increasingly viewed as chains that limit a nation's ability to respond to emerging threats. As the United States seeks to counter a rising China, and as Russia seeks to reclaim its sphere of influence, the perceived need for flexibility is overriding the collective need for stability. Nations are no longer asking, "How can we reduce our arsenals to ensure peace?" Instead, they are asking, "How can we modernize our arsenals to ensure we are never caught unprepared?" This is the death of the stability doctrine. In the old world, the goal was to reach a point of equilibrium where no one would dare strike. In the new world, the goal is to achieve technological superiority, to develop weapons so fast, so stealthy, or so precise that the enemy's ability to respond is rendered moot. When you pursue technological dominance, you inherently undermine the very concept of a treaty. You cannot agree to limits while simultaneously racing to develop hypersonic glide vehicles that bypass every defense system ever built. You cannot commit to transparency while your strategic advantage depends on absolute secrecy. As these legal frameworks dissolve, we are losing more than just paperwork. We are losing the shared language of nuclear restraint. We are entering a wild west of nuclear geopolitics, where the only law is capability, and the only deterrent is the speed of your trigger finger. The rules of engagement are not just changing, they are disappearing, leaving us to navigate a storm without a compass. 2024, Geneva, Switzerland. As the sun sets over the Lake Geneva, the quietude of the diplomatic quarters feels increasingly surreal. We have spent this journey tracing a path from the chalkboard equations of the 1900s to the terrifying, automated reality of the 2020s. We have seen the atom transition from a scientific curiosity to a tool of total war, a pillar of global stability, and now, a volatile variable in a high-speed technological race. But as we stand at this precipice, we are forced to confront the most haunting question of the modern age. Can humanity actually coexist with the power of the atom? For nearly 80 years, we have lived under a grand, unspoken paradox. We have relied on the threat of total annihilation to maintain a fragile peace. We have built our entire global order on the foundation of mutual assured destruction. The idea that the only way to prevent a nuclear war was to make the cost of starting one so absolute that no rational leader would ever pull the trigger. But the paradox is breaking. The stability we once enjoyed was predicated on human decision-making and predictable, slow-moving hardware. It was a world of seconds and minutes, time for leaders to talk, for hotlines to ring, and for human intuition to override the impulse for retaliation. But that luxury of time is evaporating. As we integrate artificial intelligence into command and control systems, and as hypersonic missiles shrink the window of response from 30 minutes to 3, we are handing the keys of our survival over to algorithms. We are moving toward a world of automated deterrence, where the speed of a machine's calculation determines the fate of a civilization. In such a world, a software glitch, a sensor error, or a cyber attack doesn't just cause a crisis, it triggers an unstoppable cascade. The final verdict is not a single sentence, but a choice between two divergent futures. In one future, we recognize that the atom is a force that defies the traditional logic of war. We realize that in a nuclear age, there is no such thing as victory, only varying degrees of catastrophe. This path requires a radical evolution of human consciousness, a move away from tribal nationalism and toward a global stewardship of our collective survival. It requires rebuilding the shattered architecture of diplomacy and recognizing that our technological prowess has simply outpaced our political maturity. In the other future, we succumb to the gravity of our own nature. We continue the race for technological superiority, believing that we can outsmart the physics of destruction. We continue to view security as a zero-sum game, where one nation's safety is built upon another's vulnerability. In this scenario, we do not die by a single, grand decision of a madman, but by the friction of 1,000 small errors, 1,000 broken treaties, and the cold, unfeeling logic of a machine that reacted too quickly to a ghost in the system. The history of nuclear weapons is not just a history of physics or politics. It is a mirror held up to the human soul. It reveals our capacity for breathtaking brilliance and our terrifying capacity for self-destruction. The atom hasn't changed. We have. The question is no longer whether the atom is powerful enough to destroy us. The question is whether we are wise enough to live with it.